education. So, well, we are very excited to hear her presentation and to experience her the activities that she designed. Well, I will leave it to you, Kelly.
Okay, wonderful. Well, thank you all for being here. I'm gonna share my screen and then move this someplace else so I'm not looking at it. Great. And everybody can see this and it looks okay? Or not that it looks okay, but you can read it. So, okay, wonderful. Thank you again for being here. So some of you actually might know that I've been taking a course on astronomy and colonization through the University of Toronto. And in one of our sessions, we discussed the issue of land acknowledgements. And in Canada, these are fairly commonplace. And it's become more of a box to check when you're running an event, rather than like a genuine statement of recognition that's then followed by some attestation of action. And in the US, by contrast, really, this practice is still more or less on the fringe. So I see a lot of value in continuing doing it. And so I'd like to just recognize that the Center for Astrophysics and its affiliated campuses sit on the traditional and ancestral lands of many indigenous peoples. In Cambridge, these include the Massachusetts and nearby Wampanoag people. In Arizona, there's the O'odham, Papago, Opata, and Sobai Prairie people. And in Hawaii, the Native Hawaiians who are still really not federally recognized as indigenous nations. So I'd like to hold space for the really painful histories that these people have endured as we work to understand how we are all complicit in that history. But this statement alone really is not enough. I'd like to encourage everyone here today to familiarize yourselves with the Native peoples who originally inhabited the land on which you now work and live. To educate yourself on the ongoing struggle against the colonialist structures that have so impacted their lives for centuries, and to really seek out ways in which these peoples and cultures have survived and the ways that they have reclaimed joy. As for me, it's my ultimate goal to find many ways to interlace and interweave the educational materials that I produce with the history of Indigenous people in the United States, and to present their ways of living with nature as necessary and complementary ways of knowing the universe. So with that, I'm just gonna take you through a short agenda of what we're gonna be doing today. So I'm gonna spend a little bit of time motivating this work and giving some sense for the intersectional framework that I've had in the back of my mind throughout the process of creating these activities. Then I'll put a link to a Google Doc containing my work, and I'll have you all into breakout rooms. And while you're there, you'll be assigned to a particular chunk of materials, and you'll have time to go through that chunk in your groups. I'll give you all some questions to guide your thinking along the way, so you don't have to worry too much about that. After about a half hour or 45 minutes, I'll bring everybody back, and we'll have some time to debrief and to give feedback. So I don't know if you've noticed, but this is really more for me than it is for you. So I really appreciate you guys all being here today to help me out with this. So just a little bit of introduction. I created this in collaboration with Mary as partial fulfillment of the broader impact portion of one of Tony Stark's NSF grants. That particular grant included a focus on cluster science and gravitational lensing, among many other things really. But an important part of this grant was actually to maintain the operations at Magellan for the Parallel Imager for Southern Cosmology Observations, or PSCO, and to use some of their cluster images for educational purposes through the microobservatory. So I created this curriculum to reflect, at least in some broad strokes sense, these main science goals. And the most fundamental part of that was really an exploration of gravity, and that's become the foundational element of the work that I'm sharing with you today. So what I've created is actually a curriculum in 3 parts, but we'll only be working with 2 of them today. The first is dealing primarily with Kepler's laws and has the students use the PhET online computer simulations to explore how this works at different mass scales in our solar system. Part 2 leads students through the thought process behind Vera Rubin's discovery of dark matter, connecting it back to the previous part on Kepler's laws using the project star nomogram. And finally, the third part, which again, we're really not looking at today at all, takes a deep, deep, deep dive into gravitational lensing and incorporates PSCO imaging into the mix. So the title of this talk, as you might have read, is a quote from Mae Jemison's TED Talk, Teach the Arts and Sciences Together. I've intentionally made this work cross-disciplinary in as many places as I thought I could get away with it. And this includes things like the history of science, science ethics, STEM identity, current events, the interaction between astronomy and Native people, and really so much more. The fields that are shown below this are ones that are featured in the third part of the curriculum, which I haven't finished and is arguably way too long. So in addition to creating a deliberately cross-disciplinary piece of work, I was operating under a very specific intersectional framework for diversity, equity, and inclusion. But intersectionality can be kind of confusing. There's a lot of different definitions for it. So I want to take a closer look at what that actually means. Now, as a concept, it's a pretty old one. Sojourner Truth at the Ohio Women's Rights Convention in 1851 gave her Ain't I a Woman speech and talked about how the intersection of her race and her gender necessarily removed her from all, from certain spaces and from certain rights. And then many years later, Bell Hooks wrote, "The struggle to end racism and the struggle to end sexism are naturally intertwined. That to make them separate was to deny a basic truth of our Black women's existence, and that race and sex are both immutable facets of human identity." Kimberly Crenshaw in 1989 and 1991 actually coined the term intersectionality in a work describing Black women's experiences in a few seminal court cases. And she describes it as a way of framing the various interactions of race and gender in the context of violence against women of color specifically. Intersectionality isn't a static theory, it's ever evolving. The early constructions of intersectionality were, according to Cho in 2013, a jumping off point to illustrate the larger point of how identity categories constitute and require political coalitions. And finally, Prescott-Weinstein describes intersectionality as not merely the intersection of multiple identity axes, but also a framework for considering what it means to live at the intersections of identity in the context of acknowledged, very real power dynamics that determine the everyday of people who have traditionally been forced into the margins. And this in particular really necessitates some amount of action, some political action when operating under this kind of framework. So for me, intersectionality is not just about intersecting identities. It's about challenging the ways that hegemonic structures of power and privilege that make up the backbone of society. To authentically work within this framework is to actively and purposefully subvert that reality. And Prescott-Weinstein presses us a little bit more to think about this in practical terms. Scientists must ask themselves, what do we ask people to give up in order to succeed? What requirements about social background, about clothing, hair, English dialect, neurotypicality, state of disability, and gender normativity do we need to excise from our community standards? So when considering these questions, I like to use this construction of an intersectionality framework. I've adapted this from Havinsky's 2012 paper, where it's actually presented as a framework for analyzing policy. And it contains several intersecting, overlapping, intertwining categories that really force me to rethink the way that I'm approaching my content creation. The names of each category that are listed here can be a little jargon heavy, and I won't go through what they mean theoretically, but here I've listed what each one means to me and how I've attempted to implement it practically. So intersecting categories is really this idea of cross-disciplinary work. Multi-level analysis requires the intersections of science and society very specifically. When you're talking about power, you're talking about providing space for a redistribution of classroom power. In reflexivity, make space for discussion, redefine who constitutes an expert. In time and space, really placing people and concepts in their socio-historical context. And then diverse knowledges presents an alternative way of thinking and knowing as valid and important. And then social justice and equity is really more of a question for myself. What does it mean to have an equitable classroom? How are we challenging traditional social and power relations, as Havinsky said in 2014? But in addition to this intersectional framework, I also keep in mind these main components of multicultural and inclusive STEM classroom framework. Some of you may remember an EIJC session from 2018 that John Lewis, who's one of the grad students at the CFA, and I put together on inclusive teaching strategies for STEM classrooms. And this REDIC in 2006, this resource was our primary source for that we drew from for that presentation. But I really like this framework. It has 5 main elements, and again, I won't go through the theory behind them, and I've listed them here and how they manifest in the work that I'll be showing you in a little bit. Now, I don't want to read these to you because I think I've read enough to you already, but you'll see there's a lot of overlap between the intersectional framework that I've been using and this inclusive framework. And moreover, in the REDIC paper, they call out that although not all effective teaching is inclusive, all inclusive teaching is effective. And I would argue that all intersectional inclusive teaching is effective as well. So one of the key takeaways from this is that when you aim for those of your students who exist at the margins, you're inevitably going to serve the vast majority of the students in your class, if not by accident. So I will be assigning you all into 4 breakout rooms, which I'll send to you in a moment. And when I do that, pay attention when you get the invitation for the room, and that'll say the breakout room number that you're in. And I'll copy all of this into the chat so you don't have to worry about it. But each breakout room will get a certain chunk of the document that I will link you to as well. So as you go through these activities, here's just some questions to keep in mind. Again, I'll copy all of these into the chat so you have access to them. But these include questions like, for what age group is this most appropriate? And what would you need to change in order to make this appropriate for 1 or 2 grades below that? What other scaffolding or structure would improve these activities? What do you think would make it more clear? Can this be done in a single class period? Or in the class periods that I've delineated in the document that I'll send you? And what other modalities or learning styles could be included, and where could they be included? What further connections to the arts or the humanities could be included as well? Where are the knowledge gaps? What assumptions am I making that I really shouldn't be? And are there more connections to the next generation science standards that I should include that I haven't already included? And really, please feel free to add any other questions that you might want to discuss, either in your breakout room or when we come back to the full group. So I will stop sharing now so I can set up, oops. Yep. And I will set up your breakout rooms. Let's see. All right. So before I do that, let me share with you. So these will be the assignments for the different groups. And there are 4. It says breakout room 1, 2, 3, or 4. And please go according to that. The questions. And then if people don't have access to things, I set it so that everyone with this link should have access. If you don't have access, please let me know and I will fix it as soon as I can. Google occasionally tricks me. So I will be popping into the different breakout rooms as we go forward. And hopefully you all enjoy yourselves. Have fun. I will see you in, I'll give you a, so as a tip, it might be useful to spend the first 5 minutes of this breakout room session just reading over the part of the section that you're supposed to be looking at. You probably already figured that out, just as a reminder. And then spending the rest of the time actually going through the document in your group. And collaboration and group efforts are encouraged, if not required. Yes, and I will give you a 10-minute warning and a 5-minute warning, and then a 1-minute warning to come back to the group. So wonderful. have fun. If I didn't get this to you, or I forgot, or you forgot, or you'd rather have it again, there's a Google Doc where you can put written feedback instead of verbal feedback. Let's see if this is actually being recorded before. Yes, it is. Great. Okay. And yeah, I don't know if someone just wants to start talking, that's fine. Or if you'd like to raise your hand in the participant box, you can do that too. I'll keep an eye on it. Don't all rush me at once.
I want to hear from kind of, it would be helpful to hear from the earlier groups first, just because they had some of the scaffolding that we missed at the end of the activity. And I don't know whether that's possible.
Well, so group one who had those early pages were Phil and Max and Wendy and myself. And maybe Phil had wanted to share something. It was, we thought it was really cool. We really liked the simulation. We thought it was a little hard. We kind of led to a conversation about where physics shows up these days. And sometimes it's early in high school and sometimes it's very end of high school. So depending on what you've had for math, that can be an issue. And then we talked a little bit about the standards and making sure those are included. And then Phil, did you want to share what you were trying to share with our group?
Oh,
it's still disabled, Kelly.
I think we lost Phil.
No, he's there, but he can't share.
It's still,
Oh.
I'm still disabled here.
You should be able to do everything now. You're on co-host.
Oh, that's better. Okay, my question was if this is physics in high school, the students have some algebra and can actually do, use some equations to do things. If it's if it's like physics first or it's something in middle school, their command of algebra is going to be really, really minimal. And the way the approach that I would use initially for students, especially for those who are in younger grades, is to give them data about things that they know about. Like they know that the planets are different distances from the sun and that they have different periods. The ones that are far outside are going slow and the ones that are inside are going fast. And so something like this, being able to graph, here we go, being able to graph the period versus the distance, so period in years versus the semi-major axis distance, for the planets gives them a straight line. And if they do it for Jupiter's moons, they also get a straight line. And if they do it for the Earth, the moon, and the Earth satellites, they'll also get another straight line that's parallel to these in a different place. And so the question is why that clearly something's the same, that they're all straight lines that are parallel. What's different about the system? And the thing that's different about the system is essentially the mass of the central body. So this allows you to talk about how the mass affects the slope of this line. And then you have a way to measure mass, comparing it to the Earth or the Sun or to Jupiter, without moving directly to Newton's gravitational equation. Because this is what Kepler had. He just said they were proportional. The period squared to the, whichever direction it goes, the period squared to the distance cubed was proportional. So I thought that the graphical approach, even though people don't use log paper very much anymore, would still be really useful as an introduction, because it would tie things that people are familiar with, the planets in order, the Earth, the moon, and satellites, to other systems. So,
Thank you for that. That's a really great suggestion.
so yeah, that's a way to get to the younger or less less mathematically able students.
Was there anything else from group one that you guys wanted to bring up?
Well, Sue was talking about reading level. Oops.
You're on mute.
Oops.
At some point when you get closer and ready to want to publish this, you should spend a little bit of time looking at readability. Unfortunately, even if it's high school, reading level has to be, we always put high school things at about an 8th grade reading level.
Okay.
But I thought this was a teacher's guide. So
In part.
if this is for teachers, then there has to be like a separate part for students.
Who are the worksheets? Who are the questions for then?
It's kind of like it does a dual purpose functionality. So a lot of it is for the teachers, but the worksheets and stuff are all for the students. So if you're talking about the worksheets themselves, then that would be something that I need to look at in terms of readability.
Yeah. Okay, I'm sorry.
Yeah,
But even to Sue's point, you might even want to address that anyway, even if it is a teacher's guide, because very often you might have teachers who are unfortunately being put in a position where they're teaching out of field and they still have to teach it, but it's not their background. So it might be helpful anyway.
Yeah, that's a really good point. So thank you. Anything else from group one, or should we move to group two? Okay, group two. Do you have anything you'd like to say?
Well, I made tried out the nomogram, and I had a few mistakes and realized that this is actually kind of hard to use for somebody who's not used to it. So we had this suggestion that the teacher do a demo of this with either a huge poster, like blow it up to poster size and put push pins at the different points and use a piece of yarn or string to mark out where they go.
Mm-hmm.
Or if you don't have a poster printer in your classroom, you could just project it on the screen and then have students come up and put like a dot on the screen and hold the yarn there. So the idea is just to make it something physical and bigger and easier to read. And then I like the idea, one of the things that stumped me, because I'm, not it's been years, I forgot to look at the different masses. So you have to make sure that you're starting from the right point, the sun, the clusters, the earth, the moon, etc. So that was my suggestion.
I love that suggestion. Thank you for saying it out loud. I appreciate it.
We also had some things about the high level context and the amount of text and vocabulary jargon in there, and that would need a fair bit of scaffolding. And if yes, this is a teacher guide now that we realize that, but at the same time, some of the things that would be for the students, there's an awful lot of text there, and very often when there's a lot of text with a lot of vocabulary in it, students come away with not knowing what they're supposed to take away from it. And Jamila has done a great job of putting all of this in the feedback document. So I don't know if there's anything else that she wanted to mention, because she's written it all in there for you.
Yeah.
I mean, no, I thank you all for the awesome discussion. I think one other thing we can highlight maybe, and I guess this was kind of mentioned before too, but since, certainly not in my school, but since so many high schools don't have any actual astronomy classes, it would be really cool to be able to connect, yeah, everyday physics to what you can actually, some of the similar mechanics apply here on Earth to what's out in space. So that maybe offers a really cool opportunity for labs. So one thing we were talking about was, okay, if you've got orbital motion, well, the same, sort of same equation that you can use to describe a wheel spinning, you could use to apply to Earth rotating, which is really cool. And that could, have some cool labs that students could do in class. So that was another thing we talked about.
Yeah, and one other thing that we mentioned, speaking of equations, is when you have an equation to put the units up and what the variables are. So if people don't know what t is, because I think students have a lot of trouble with those units. But we really liked it. I mean, we thought it was a great activity, and it's kind of fun to see, that it actually works, like always in physics.
Thank you for that. I think something that you guys mentioned, like tying things back to how, or more like a kinematic version of how things move in on Earth and in space and how they're all connected. I think that's very related to group 3, perhaps. So if you guys wanted to take up the reins.
We had a good discussion. I think one of the things that we didn't that we missed at the beginning was the structure at the first few pages of kind of how you had kind of envisioned the classes and lab going, but that was helpful. We kind of got that at the end, and so just reading our section and not reading the previous sections, it was a little confusing as to what the background knowledge was, but seeing that they go through these other sections kind of first would be helpful, because the concept in our section of galaxy rotation curves and spectroscopy just thrown at them without any previous knowledge was kind of, we were thinking might be, a lot unless they had, a course on it or some of that background knowledge from previous labs. One thing that I had mentioned in the breakout section was how I'm a very visual learner, and one of the activities in our section was like getting students arm in arm, and they're moving around kind of the stars in the bulge and then out in the spiral arms. And I had to read that a couple times. So my suggestion was like putting a picture of that setup with the students would be helpful for the teacher, or even we even said maybe even you creating a demo video for the teacher, because the same concept, the same thought came up that I think Cynthia brought up, that if you are a general education or general science teacher, this is kind of advanced if you're not an astronomer. So as much explanation for the teacher would be really important. And I don't know if others have comments in our section.
Just a quick comment that for that video part, we suggested that maybe what you could do, I mean, this depends on the school's resources, of course, is actually record the first session where the students are doing the activity themselves without actually putting points on a plot or anything like that, just actually doing the activity and taking the time to sort of to build that physical sort of world. And then the next session could be that video being replayed on a screen in the classroom, and then students actually getting down to okay, let's make plots out of this. Now we're observers rather than planets and stars, whatever.
That's a nice idea. I like that a lot. Anything else from group 3, or should we on down to group 4?
Well, just a quick suggestion. So we, right at the end, when just a couple of minutes left, we started thinking about sort of ways to connect it to the humanities and arts a little bit more. One of the artistic activities we thought of was actually using the spectrum images that you have there, which are lovely, by the way, really nice way of explaining electromagnetic spectrum. To use them for painting, so you could have students construct each element / color using the colors that are represented in their spectrum. So nitrogen would be a lot of reds and oranges, etc. And then the other ones will be different things. And then they can paint, I'm painting with hydrogen in the sky and then nitrogen in the sun or whatever. You could just do something like that.
That's really
We
creative.
gave that very little time. So
Yeah, and I think I brought up if you want to get really messy, you can get students in booties and put like different color stars on their feet, and they can walk around in the circles.
I really
That'd be
love
very messy.
Very
Interesting
cute.
art.
Yeah. In the interest of time, perhaps let's go to group 4. You're muted, Mary.
I'll summarize group 4 and let Erica and Gerhard, who were the other 2 members of group 4, who did most of the talking, weigh in on how well I've summarized. But I think some of the issues that came up with group 3 were the same by the time you got to the last 8 pages of those, where the first thing was to worry about, has there been enough scaffolding to get to the point where we were for people who were looking at this cold? But now we've heard some of that scaffolding that's up there. There was some, again, feeling that it was appropriate for high school, and probably that the vocabulary is difficult. Agreement with some of the other groups that there's a lot of, for example, even in footnotes, where in section 3 you're talking about kinetic versus potential energy as different ways to think about it, but like without getting into those ideas, it might be too much. So there was some concern about that I've heard from other groups around really thinking about when it's necessary to introduce new vocabulary and do that. So in the 4th section, kids are preparing to look at Vera Rubin's real data and rotation curves by kind of making predictions about what different rotation curves would look like. Roy, this came from our original Galaxy Hubble law activity, the idea of making predictions before you do it. But definitely both Gerhard and Erica looked at that first prediction around random motion, when everybody been set up to be thinking about rotational motion, and it was very confusing with regard to, you had this idea of drawing random motion, and you had these vectors going every which way, but your plot doesn't allow for directionality. It only allows for speed. Anyway, it kind of threw everyone, and Gerhard was concerned it actually takes what understanding you've built up and completely confuses kids before you get. So anyway, we need to think about that random motion graph. I think the main thing that our group was concerned about was to really think about the amount of time kids are spending mechanically graphing things versus the time they're spending making meaning of what the graphs signify. And so there was some question about whether, you need more time for all that if you're having them graph these several different scenarios and then the real data, and then only at the end of the class do they have a little bit of time to say, okay, what does it mean? Erica had a suggestion of maybe the homework, there's a homework for that night, which is what does it mean? And then a discussion at the next class about what does it mean, because you really want to spend more time and maybe less time on the actual, maybe just presenting, even though we want kids to do activities, we want them to do the thing to really think about. In this case, is it more important to have them spend time interpreting the meaning of the data as opposed to constructing the data? So I think that, oh, and then we did have a discussion about the actual intersectional part of this particular piece, which is some questions about how science works, the social nature, you have those little vignettes about how Vera Rubin's work was not accepted by the scientific community at the time, and the work of her students, this big, Gerhard was basically, as a sociologist, noting this is, pointing out that people like to stick to their theories even in the face of evidence. But at the same time, and elucidating the difference between ideal science and real science, the way science really happens. So we like that. I think, I don't know, Gerhard, you might want, I don't know that I'm capturing your comments here. Gerhard did bring up Phil's activity called Book Bits, where he gets students to look at these little bits of a book, and they form their own theory about what the book's about, and then later looking at more they stick to their original theory for a really long time, even as they get more evidence. So we like the idea of looking at the really how science works, and the kind of that the real way science works is different than the ideal way science works. But I think Gerhard was also wanted to make sure that it was acknowledged that still real science is able to accommodate changes in perspective.
Yeah, you could compare it to religion, for instance, where revision is very little accepted to holy books, like the Bible or the Quran, and whereas science is a social system of knowledge that is open to revision. I mean, that's a very kind of broad implication. I mean, I don't know if you want to do it there, but because you could do it anywhere when you talk about the differences of, the different social systems of knowledge that we have as humans, and how science is different from others, like religion or politics, and what that means for the openness to revision, and what that means about beliefs in truth, and what the nature of truth is that comes out of the scientific process, as opposed to the nature of truth that comes out of the religious process. So that's a very kind of general connection.
Absolutely. Well, thank you guys for sticking with me for so long. And thank you for all of your feedback. I took absolutely no notes because I'm going to listen to everything again several times over. But if you'd like to add anything to the Google Doc, please feel free to do so even later today or tomorrow or next week, whenever you're thinking about this. Thank you. Yeah. thank you so much for all of your feedback and for really taking this into your lives and hearts and minds. And yeah, wonderful. I hope you all have a really great day.
This was great. It was like our old seminars where we would really go over materials and we'd all be together and we'd say, you know, so I really liked that aspect. This was great.
And I'm sorry, I need to go off topic for 1 second, but I want to have everyone say thank you again. But Gerhard and Phil, I need you to stay on the call for 5 minutes. But go ahead, let's go back to Kelly.
I love it. Yes.
You have a lot of courage to present to this group. Sometimes people have been a little harsh in the past, but they weren't today. So,
Well,
at least maybe.
Yeah, the thing is we all already assume it's amazing. So we assume that you already know it's amazing. So then we're like, well, let's just jump in with all the little stuff. But if we didn't say that, it's amazing. You know, it's a great start. It's really, really, you know.
It's labor of love.
Well, thank you, Kelly. And this is a great demonstration and presentation. And yeah, I hope that we can keep our conversation, and we're looking forward to the progress we made with this curriculum. And thank you everybody else for joining us. We will keep you updated. We will keep you posted for the upcoming speaker in December.
Are we not having virtual swap?
Oh, how do we do that? Do we mail to each other? Think about that.
We could do Secret Santa or Secret something else. Wendy's on. Wendy.
Oh, Wendy, you are muted.
So yeah, something in the winter. We already actually have a speaker for December and January. So maybe February we might think of a midwinter fun event via Zoom.
Yep.
I like the idea of a secret, not Santa.
Yeah. And you could send it, right?
Mm-hmm.
You
just
bring
shows
it
up
to
at
a
your
different town so that it's not postmarked from your town.
Or send it via
Yeah.
the internet.